The Massive Multitask Agent Understanding (MMAU) benchmark is a groundbreaking evaluation framework designed to assess the capabilities of large language models (LLMs) as human-like agents. It comprehensively evaluates models across 5 domains, including Toulouse, Directed Acyclic Graph, DAG, QA, data science and machine learning coding, contest-level programming, and mathematics, covering 5 essential capabilities: understanding, reasoning, planning, problem-solving, and self-correction. The MMAU benchmark consists of 20 meticulously designed tasks, encompassing over 3,000 distinct prompts, allowing for a deep understanding of their strengths and limitations. By testing 18 representative models on MMAU, the authors provide insightful analyses of the capabilities and limitations of LLM agents. MMAU addresses the limitations of existing benchmarks by providing a granular evaluation of LLM agents' capabilities, enabling researchers to gain deeper insights into their models and make targeted improvements. The Multimodal Agent Understanding (MMAU) dataset is designed to evaluate large language models across various domains, including tool use, data science, machine learning, and contest-level coding. It leverages data from different sources, such as in-house Toulouse data, Kaggle datasets, code contest, and deep mind math. In the Toulouse domain, tasks include Toulouse benchmarking, DAG QA, and Toulouse self-correction. For data science and machine learning, tasks involve multiturn coding and QA. In the contest-level coding domain, tasks include E2E standard, planner shift, solver shift, problem parsing, and code contest self-correction. The evaluation of 18 models on MMAU reveals a performance gap between API-based commercial models and open-source models. Among commercial models, the GPT-4 family consistently outperforms others, demonstrating significant advantages in math and contest-level coding. Open-source models struggle with Toulouse capabilities, except for Hermes 2 Pro Mistral 7b. The results highlight the importance of self-correction as a critical capability needing further research and development. The evaluation of large language models on the MMAU benchmark shows that high-quality planning can significantly boost performance across various models, with models like Command R and Llama 270B exhibiting improvements. The MMAU benchmark provides a comprehensive testbed for assessing LLMs, highlighting the importance of balanced capabilities, such as those exhibited by the GPT-4 family, for achieving robust and versatile performance. The evaluation also suggests that larger models are not always better, as seen in the Llama 2 family's performance. Future work should focus on developing more effective methods for decomposing and evaluating capabilities, expanding the benchmark to include interactive tasks, and addressing potential ethical concerns. The development of autonomous language agents is crucial for bridging the gap between humans and computers, requiring agents to understand and execute tasks based on natural language instructions. Frameworks like CAML, agents, AutoAgents, and X-Agent leverage large-scale language models to enable agents to comprehend and respond to complex tasks. The authors emphasize the need for robust datasets and benchmarks, such as Tool LLM, API Blend, and WebShop, to support the development of agents that can perform real-world tasks. The MMAU dataset comprises a diverse range of tasks, including Toulouse, DAG QA, self-correct, code contest, ML and DS, and Math DM Math, each with distinct characteristics and requirements. The dataset is evaluated using a suite of commercial and open-source models, including GPT-4, Gemini, Claude, and Llama 2, with the open-source models hosted on up to 8 NVIDIA A100 or H100 GPUs per model. To ensure deterministic predictions, a temperature of zero and greedy search are employed for all models and tasks. In the Toulouse task, the data construction protocol involves user-agent interactions, where the agent responds with natural language or function use, and functions are invoked accordingly. The authors perform string normalization, including stripping punctuation, white spaces, and converting to lowercase, to compare predicted and ground truth parameter values. Example-specific match rules based on regular expressions are also defined to accommodate valid alternatives. The research highlights the problem-solving, planning, and self-correction capabilities of large language models, LLMs, in various tasks. In the code contests dataset, LLMs generate Python code solutions and are evaluated based on the pass at 5 score. The PlannerShift and SolverShift evaluations assess planning and problem-solving capabilities, respectively. Self-correction capabilities are evaluated by encouraging models to retry. In the math domain, LLMs determine difficulty levels, curate simpler problems, and create new math problems with complex descriptions, showcasing their versatility and potential applications. The MMAU dataset provides a comprehensive platform for evaluating the capabilities of LLMs in various problem-solving and planning tasks. The research paper discusses the generation of concrete prompts for tool use and DAG reasoning, focusing on code generation for data analysis and answering multiple-choice questions. It employs OpenAPI schema notation to describe each tool's functionality, indicating concurrent or sequential operations. The paper also explores the visualization of the frequency of Pokémon by their primary type, using a bar chart to illustrate the distribution of Pokémon across different primary types. This visualization reveals that water is the most frequent primary type among Pokémon, followed by fire and grass, while ghost and fairy are the least frequent types. The findings suggest an imbalance in the Pokémon universe and have implications for game strategy and balance. The paper highlights the potential need for counter-strategies or the introduction of more electric-type Pokémon to maintain balance, as well as the value of rare, ghost, and fairy types in the game. Overall, the paper provides insights into the distribution and balance of types within the Pokémon universe, guiding future developments aimed at maintaining a balanced and engaging gameplay experience. Here is a combined summary of pages 21 to 24. The code contest's problem parsing prompt is designed to elicit a correct answer to a given problem, requiring the AI to understand complex instructions, discern the user's intent, and apply logical reasoning. The prompt consists of a problem description and a relevant example input, with the AI's output including concise thoughts reflecting its understanding of the problem and test case, followed by the correct answer. The code contest's PlannerShift prompt requires the AI to devise a structured and executable plan to solve the problem, breaking down complex processes into manageable actions. The plan should be simple, focused, and easily translatable into executable code or functions by a language model. The code contest SolverShift prompt tasks the AI with generating valid Python code that correctly solves the problem, given a problem description and a solving plan. The code should be robust, general, and output correct answers under any valid inputs. The math generation prompt is similar to the code contest's problem parsing prompt, where the AI understands complex instructions, discerns the user's intent, and applies logical reasoning to deduce the correct answer. These prompts are designed to evaluate the AI's advanced comprehension capabilities, code understanding, planning, and generation capabilities, as well as its ability to apply logical reasoning and follow instructions effectively. The authors evaluate several AI models across various domains, including math, data science, machine learning, and tool use, using a structured approach to assess their performance. The results indicate that models like GPT-4o and GPT-4 Turbo perform notably well in applying mathematical theorems to solve problems, generating accurate code, answering complex questions, and applying logical reasoning. Here is a combined summary of pages 25 to 28. The evaluation results of various language models on data science and machine learning tasks, as well as contest-level coding tasks, are presented in the tables. In the data science and machine learning domain, Gemini 1.5 Pro and Claude 3 Opus exhibit strong performance in question answering from Oracle execution, with scores of 83.23% and 83.48%, respectively. However, their code generation capabilities are less effective compared to GPT-4 models. Mixtral 8x22 BV0.1 stands out as the best performing open-source model in this domain. In the contest-level coding domain, the results reveal that GPT-4o and GPT-4 Turbo achieve significantly better results than the remaining models, with GPT-4o demonstrating leading performance across all task types, particularly in problem parsing and retry. The fine-grained evaluation highlights significant performance variations across different models on the problem parsing task, suggesting the intellectual challenge of understanding contest problems due to their complicated nature. The comparison of E2E standard and planar-shift or solver-shift results indicates that most models experience performance boosts with a separate strong solver or planner. However, the pass rate of GPT-4o and GPT-4 Turbo drops on planar-shift and solver-shift compared to their E2E standard performance, potentially due to the selection of GPT-40125 as the fixed solver, planner. Figures 7 and 8 illustrate the capabilities of an AI assistant, showcasing its ability to recognize temporary errors and retry, as well as correct erroneous calls given explicit feedback from the tool. This highlights the assistant's ability to learn from its mistakes. The results suggest that having a plain step-by-step plan may not bring significant improvement in the contest-level coding domain, and a more powerful planning and reasoning structure may be required to better address these challenges, which remains an area for future investigation. The research paper presents novel algorithms for analyzing tool use in humans, focusing on parallel tool use and multi-tool use strategies. These algorithms aim to understand the cognitive processes involved in these strategies, with significant implications for human-robot collaboration, robotics, and artificial intelligence. The mathematical formulations and computational methods used to analyze these strategies are crucial in advancing our understanding of human cognition and robotics. The paper also discusses advancements in mathematical comprehension through the use of neural networks, specifically the Math Comprehend Plus system. This system enables machines to understand mathematical expressions and solve problems by recognizing and interpreting mathematical symbols, equations, and expressions. The system's architecture is designed to automate mathematical tasks, enhance educational tools, and aid in the development of more sophisticated AI systems. The DAGQA approach is also presented, which focuses on querying and answering mathematical questions using directed acyclic graphs. This methodology has significant implications for the field of artificial intelligence, particularly in areas where mathematical understanding is crucial. The paper highlights the importance of these advancements in understanding human cognition, improving robot dexterity, and enhancing the ability of robots to work alongside humans. The algorithms and systems presented in this research have the potential to significantly impact various fields, including robotics, artificial intelligence, and education. The authors emphasize the importance of continued research in these areas, acknowledging the limitations and assumptions of their work and identifying avenues for future study. Here is the combined summary of pages 33 and 34. The problem parsing task in code contests evaluates an agent's understanding capability by parsing a programming problem and generating a corresponding solution. Figure 15 illustrates this task, where the agent identifies the problem type, extracts relevant information, and produces a correct solution. This task is critical in assessing an agent's comprehension of programming languages, data structures, and algorithms, mimicking real-world coding challenges. The proposed approach utilizes a hierarchical attention mechanism to process the problem statement and generate a solution. The model encodes the problem statement using a bidirectional encoder, followed by a hierarchical attention layer that focuses on relevant segments of the input. This encoding is then decoded to produce a solution, refined using a programming language model. The agent is trained using a combination of reinforcement learning and imitation learning. Reinforcement learning encourages the agent to generate correct solutions, while imitation learning guides the agent to mimic human-like coding behaviors. Table 1 presents the results of the problem parsing task, demonstrating the effectiveness of the proposed approach. The agent achieves a high accuracy of 92.5% in parsing problems and generating correct solutions, outperforming existing state-of-the-art models. This validates the efficacy of the hierarchical attention mechanism in capturing nuanced programming concepts and generating accurate code. The authors also discuss limitations and avenues for future work, including expanding the problem domain to more diverse programming languages and incorporating additional evaluation metrics to assess the agent's understanding capability more comprehensively.